Now let's talk about the convergence of a function at a point. So here's the definition. First, we need a function so that we can talk about its convergence. And also we have to have a point. We need a point so that we can talk about the convergence of this function at this point. So let f from AB interval to R be a function, and let C be a point. Then here is the definition. We said that f of x converges to a real number y0 as x goes to c. So the condition is x goes to c, and the limit, the place, the number where the function converges to is the y0. So y0 will be the limit, and the condition is x goes to c. So we say this is the case if the following logical statement is true. And before looking at this logical statement, that's also similar to the convergence of sequences. Let's first look at the idea of convergence. So here's the idea of convergence. Intuitively, the idea is that when x gets very close to the point C, then f of x should get very close to y0, which is the limit or the value that the function converges to. Yeah, and similar to the idea of sequences, basically this can be interpreted as whenever, no matter how small an arrow is given, so the arrow is epsilon greater than 0, then there is as long as x is sufficiently close to c, then f of x should be f of x and y0, the difference between f of x and y0 should be less than or equal to the arrow epsilon that is given. So in words, actually, for every given arrow epsilon greater than 0, if x is sufficiently close to c, mathematically this means that x minus c absolute value will be less than or equal to at delta. So yeah, actually I should put it equal to here. And if this happens, then the difference f of x and y0, which is f of x minus y0 absolute value, will be less than or equal to the arrow epsilon. So let's go back to the logical statement here. So for epsilon, look at here. So we are looking at here. So for epsilon greater than 0, the epsilon here represents the arrow that we are looking at. Then there will exist a delta. Actually, this delta will depend on epsilon, so let's put the subscript epsilon here. So there will exist a delta epsilon greater than 0, such that if f of x, if x minus c, if x and c has difference that is less than or equal to delta, so let's put the epsilon here also, indicating that actually the delta depends on the epsilon. If this is the case, if x minus c is between 0 and delta epsilon, then f of x and y0 should be less than or equal to the epsilon, which is the error. Yeah, so you can see actually the idea here is very similar to the convergence idea that we talk about in the convergence of sequences. The only difference is that for sequences, we are choosing so recall that the definition for sequences is more like a for all epsilon greater than 0, there exists a capital N, which is in the natural numbers, such that an minus a absolute value is less than or equal to epsilon for all n that is greater than the sufficient index. So here n is a sufficient index. As long as the index is bigger than, so for every epsilon there is a corresponding sufficient index n, such that the difference between the place where it converges to and the sequence will be less than or equal to epsilon whenever your index n is greater than the sufficient index capital N. And similarly here, because we don't have any kind of sufficient index, but we can have sufficient closeness. So the delta epsilon here indicates that how close you should make x with c, so that as long as the distance between x and c is less than or equal to delta epsilon, actually we'll have the function value and the value that it converges to will have arrow less than or equal to epsilon. So idea is basically parallel. The only difference is here and here. It is replaced by delta epsilon. greater than 0, and for all delta, for x minus c, absolute value less than or equal to delta epsilon greater than 0. Right, yeah, because I make many circles, so this becomes kind of like a mess. So let's erase this. Right, so this is the case, and this is the place, and yeah, this corresponds to this, and this corresponds to this. Right, so this is basically the formal definition of convergence of a function at a point. And for simplicity, we also introduce this notation. So limit x approaches c f of x. Yeah, this is kind of like parallel to the concept we talked about in sequences. Limit n goes to infinity a n. Right. So if we have f of x converges to a real number at y0 as x goes to c, then we write this notation. So this notation is a simple symbol that represents what we talk about of the convergence. Yeah, and in this case we say that y0 is the limit. Yeah, just similar to what we talk about in sequences. Yeah, there's one thing I want to mention here, I want to point out here. So actually the limit here does not depend on the value f of c. So you can see that f of c does not show up in any place in the definition, especially here. Yeah, maybe I should draw it here. Just a second. Yeah, so here we do not include the 0. Yeah, the reason is very simple, because the limit should not depend on the value of the function, because it's just a limit. The sense of limit is more like arbitrarily close to x is arbitrarily close to c, but not equal to c. That's the reason why we don't include the 0 here. Because if you include 0, then f of x will become f of c. Then that will require f of c equal to y0 no matter what. And this is kind of contradict with our intuition. But actually, when equality holds, it is co-continuous, which we will talk about in our next topic. And here, I just want to mention that, point out that the limit of the function at a point does not depend on the value f of c. So it does not depend on the value, and only depends on the values that is around x is equal to c. Yeah. Alright, so this is definition of convergence of function at a point. Let's look at one example and try to prove the convergence in some sense. Alright, so here's an example. So let f of x be the function, and it is defined by f of x is equal to x squared. Alright, so this is a function. Yeah, undoubtedly this is a function. And here we want to show that. So let us show that this limit is true. So we want to show that when limit x goes to 2, f of x will be equal to 4. Alright, so recall that what we have to do is that we need to prove for epsilon greater than 0, there exists a delta epsilon greater than 0 such that f of x minus 4, because the limit is 4 here, is less than or equal to epsilon for all 0 less than x minus. So c here is 2, and here's a delta epsilon. So for simplicity, let's ignore the delta epsilon, ignore the epsilon subindex. Yeah, this is just for simplicity. Okay, here. Okay, less than, yeah. So this is our goal. We need to prove this. And because f of x is equal to x squared, so we can also replace this part by x squared. So we want x squared minus 4, the absolute value is less than or equal to epsilon whenever the delta. So as we did in the sequences, first we have to let an epsilon greater than 0, and then we try to find a delta that is corresponding to epsilon, such that the required inequality is held under the required condition. So this is what I wrote here. Yeah, here's the equality according to my definition. So this is what we need to do. We need to find delta greater than 0 such that absolute value of x squared minus 4 is less than or equal to epsilon for x satisfying the following: x minus 2 is greater than 0 and less than or equal to delta. So delta is our goal. We need to find such delta. Yeah, for this problem, actually, we use some concept about x squared, but yeah, let me explain. So first, we need to estimate this, right? We want to make this less than or equal to epsilon under some appropriate choice of delta. So let's try to estimate this term. So you can see that x squared minus 4 is actually equal to x plus 2 times x minus 2 with absolute value. And we know that our condition, the delta can only control this condition because x minus 2 absolute value is less than or equal to delta. That is the only thing that we can control when we choose a delta. And you can see here, x minus 2 absolute value is actually here because this is equal to x plus 2 absolute value times x minus 2 absolute value. And this term we can control. And this term we have to kind of estimate. Yeah. So x minus 2 absolute value, this term can be controlled by delta. And this term can also be controlled by delta, but we have to figure out how to do that. And notice that actually if we simply set that delta is less than or equal to 1, then the x that satisfy this condition must belong to 1 and 3 closed interval. Yeah, the reason is very simple. Is because when x minus 2 is less than or equal to 1, we know that actually that means, so 2 is here. X minus 2 less than or equal to 1 means that x is between 1 and 3. Because x minus 2 absolute value means the distance between x and 2. And this condition, the absolute value is less than or equal to 1 means that this distance is less than or equal to 1. And if you go to the right by 1 unit, then you get 3. If you go to the left by 1 unit, then you get 1. So actually x is bounded by 1 and 3. So this is what I mean by saying this. Yeah. So here is for delta, but because if we choose delta is less than or equal to 1, then this is automatically true. Then x has no choice but between 1 and 3. And this is the key idea because x is between 1 and 3, so x plus 2 is between 3 and 5. So you can see for the next line. So for the same delta, if delta is less than or equal to 1, then this is the same as x plus 2, and it is belong 3 and 5. Because x is belong to 1 and 3, this implies x plus 2 absolute value is belong to 3, 5. Alright, so this is this line. And this is a key idea because when we choose delta is less than or equal to 1, then we can guarantee that x is between 3 and 5. No, x plus 2 is between 3 and 5. And the very first term here is controlled inside 3 and 5. That means this term will be, okay, so let's look at the start to here. So therefore, for delta is less than or equal to 1, this term will be less than or equal to 5, and this term can be controlled by delta. So we just write this is less than or equal to 5 times x minus 2. Because x plus 2 absolute value is between 3 and 5, so actually it is less than or equal to 5. 5 is the maximum in here. Right. And then what we can do is actually we can take delta is equal to minimum of 1 and epsilon over 5. The 1, if we take delta is equal to minimum of 1 and epsilon over 5, then because it's minimum of these two, so it must be less than or equal to either of 1 or epsilon over 5. And when delta is less than or equal to 1, then we know that we have this condition. this inequality is guaranteed. This inequality is guaranteed by choosing delta is less than or equal to 1. And for this term can be controlled by this. So yeah, you can see. Okay, so let me erase something and explain here. Alright, so because delta is less than or equal to 1, we have okay, so this argument follows from here. Because delta is less than or equal to 1, we will have x squared minus 4, which is equal to x plus 2, x minus 2, which is less than or equal to 5 times x minus 2. Okay, so this follows from simply delta is less than or equal to 1. Okay, so this is for all 0 less than or equal to x minus 2 less than or equal to delta. And the second thing is, because delta is less than or equal to epsilon over phi, therefore phi times x minus 2 will be less than or equal to epsilon for all 0 less than x minus 2 minus less than or equal to delta. Yeah. And since we take delta to be the minimum of 1 and epsilon over phi, so these two conditions are satisfied. So this inequality is satisfied, and also this inequality is satisfied. Combining these two inequalities, eventually what we get is this: for all 0 less than x minus 2 epsilon value less than or equal to delta. So this is basically what we want, right? And this goes back to what we want here.